Welcome back to the sixth and final topic in Chapter 1. In this topic, we're going to be looking at local linearity, which is a concept more than something you have to do, and we're going to be looking at difference quotients, which is actually just a big fancy word for something you already know how to do anyway. So, first, the thought of local linearity. What the idea of local linearity is if you take certain curves, certain graphs, and you zoom in really far, it starts looking like a line. So if we have the graph of y equals x squared, and we're going to zoom in, we're going to specifically zoom in just kind of right in that area. So we zoom in again, zoom in again. See how it's getting straighter and straighter? Zoom in. This looks like it's pretty much straight. Look at the x-axis here, the x scaling. The y scaling is going to be the same. The way I zoomed in, it keeps it the same. So I mean, this is 0.01 to go from there to there. So I mean, we're zoomed in a lot. We could zoom in even further, and that looks like a straight line. Like I don't even see any curve to this at all. We're actually far enough off the x-axis that we can't see it anymore because we're zoomed in that far. But this is still the same graph. And so that's the idea of local linearity. It's that if something is curved, you can zoom in and it looks flat. It's the same concept actually that we see on Earth. Earth is a sphere or close to it, you know, assuming round Earth theory and all. But I'd say it's pretty clear we can assume it's a sphere. But as we're moving around on the Earth, it seems more flat. It's because it's locally planar. Um, and so it's the same idea. So some of these graphs that are smooth, and smooth just means that you can zoom in. It's going to be linear if you zoom in far enough. We have quadratics and cubics, and really any polynomial is going to be smooth. Exponential graphs and logarithmic graphs. Cosine, sine, in addition to all the other trig functions where they're defined. So not including the asymptotes, the other trig functions would also be smooth. So what are some not smooth graphs? Absolute value functions. It has this big corner here. It does not matter how much we zoom in, that is going to be a corner. It's going to be a distinct change in that slope, and it will not look like a line. And so those are functions that happen. Other times you just have to get piecewise functions. So like here, it's not smooth, it has a corner. And even here, there's a little corner. It's really close, but there is a corner there, and those corners are called cusps. Technically, any corner is a cusp. A lot of times when we think of cusps, though, we think of this middle one where it kind of makes a corner like that where it's kind of angled and it goes up. But any corner is technically a cusp. Um, and so those are some smooth graphs. So when it's smooth, when we can zoom in and it becomes linear, we can do things like find a slope. It's a line. We can find a slope of a line. And so that's what we do. And what we use are these things called difference quotients. A difference quotient is just a slope. It's the same thing. Quite literally, a difference quotient is a quotient, that would be the division, of differences, the subtraction. A difference quotient is a slope. Um, when we're using these, and in calculus, the next chapter we're going to see this, we use a slightly different version of this equation. It's still the same thing, we just write it out a little bit differently. And so if we're going to approximate the slope of the tangent line to a curve, which is what we will do with these locally linear things, we have a curve, and if we get really close, we can get the slope of that curve or the slope of the tangent line to the curve, which is more appropriately, because a curve doesn't have a slope. Slopes are defined for lines. So we can get the slope of the tangent line to the curve, which would have the same slope. I'm using quotation marks in the air here. It would have the same slope as the curve. But for the slope formula, we use this one. It's m equals f of x plus delta x. That's a change in x minus f of x over x plus delta x minus x. This is y minus y over x minus x. It would be the same as finding the slope from 2 to 3, except instead of 3, we wrote 2 plus 1. It's f of 2 plus 1 minus f of 2 over 2 plus 1 minus 2. Same idea, except we're going to use very small increments of x. And then in the denominator, the x's always cancel each other out, so that could just be delta x down there. So just a change in x. And so by using small delta x's, we're going to get it closer and closer to the slope of what the tangent line is going to be. The smaller that delta x value is, the better approximation we will have. And so for most of what we're going to do today, we're going to use 0.01 for that difference. But that's just kind of a general rule of thumb. You make it smaller, your estimation gets better. So let's do a problem. Let's approximate the slope of the tangent line of f of x equals x squared when x equals 2. So first we need to find our points. F of 2 equals 4, we just plug it in. And then we need to add 0.01. So f of 2.01 is 4.0401. If we square the 2.01, that's what we get. We have 2 points, we can find the slope between them. It's just y minus y over x minus x. We can do our calculation, so it ends up just being those decimals, and then divide to get the slope is about 4.01. So that's the approximate slope of the tangent line of f of x squared when x equals 2. Now the thing with x squared is it's going to be different if x equals 1, or x equals 0, or x equals -1. It's not going to have the same slope as a line because it's changing. So let's look at a different one. Let's look at approximate the slope of f of x equals cosine x when x equals pi over 4. So here we have cosine, so it's trig, and we're going to see how we can do this. So first, plug in pi over 4, cosine of pi over 4 equals root 2 over 2. We know this from the unit circle. Root 2 over 2 could be rough to use in a slope formula. So that's about 0.707. We're approximating already. We round that, it's not going to make or break things. Well, now we need another number that's close to pi over 4. Well, what is pi over 4? If we do a little bit of division, we see that pi over 4 is about 0.785. We need to find something close to that. You could go up 0.01 to make it 0.795. 0.015 to make it 0.8 would be okay, but I'm just going to go up to 0.79. So if we plug in 0.79, cosine of 0.79 is going to be around 0.7038. And to do that, you just plug it into a calculator. Make sure it's in radians. That's not a value that you would have to know off the top of your head. And then from these values, we have xy and xy. We can plug it into our difference quotient, aka slope formula, and get the slope of negative 0.64. So we found 2 points that were close together, and we found the slope between them. This is largely what you're doing today. there will be some telling whether or not the function is smooth, because that's where you could find these things. And in general, we had the graphs of smooth and not smooth. Most functions will be smooth most of the time. Kind of the same thing with continuous. Instead of finding the times when it is continuous or when it is smooth, we generally notate the times when it's not continuous or smooth, because that's going to be just a couple times in a function, and everywhere else it'll be continuous or smooth. Most of the time. We could get a function that's not continuous at any point. I can show you that in class if you want. It's actually pretty simple, but it's something that you would never use anywhere, so who cares? Anyway, slopes, smoothness, and just the idea of local linearity. This is the last section of the chapter, so keep doing problems, keep asking questions, and happy mathing.